So it works. Okay. So welcome everyone. I'm Ole André Vadla Ravnås, and I work as a security researcher at NowSecure, where we use Frida for an automated analysis of mobile apps. But the reason I'm here to talk about Frida is, where this all came from. It was, as a developer, I've done a lot of, I tried to develop interoperable software for Linux to interop with closed source proprietary protocols, or closed proprietary protocols, and then I had to do some reverse engineering, and as I did this, I found myself needing tools for this. But before we go into that, I'm just going to show you what we're going to do today. We'll have the debug E on the right, which is the target process that we want to analyze, and on the left, that's us. We are the debugger. And using Frida, it's going to allocate a bootstrapper, create a bootstrapper, some code inside that other process that's hidden behind the scenes. So I don't need to think about it, but I'm just going to show you visually what's happening. And then we create a thread. Frida creates a thread in that other process. And that executes the bootstrapper, which then loads a shared library, which is our agent. And then it establishes a communications channel back to us. And across this communications channel, we can tell it to do things like, so we have a JavaScript interpreter inside here, so we can expose a set of APIs and make it do things. And I don't want to spoil too much, so I'm not going to talk about what things. But basically, the motivation behind this is that when you're doing reverse engineering, at least in my experience, you create tools because every target is different. So you can't just create one tool to reverse engineer any software, because software is different every time. They have some commonalities, but usually you want to create a tool because you figure out what kind of APIs they're using internally, and then you want to spy on those APIs. And that's where Frida comes in. So it's also an important thing to be able to do this across platforms without having to to relearn everything, or to write something platform specific every time. As you're reverse engineering, you tend to discover something, and then you adapt your tooling, and then discover something else, and then you keep adapting. So it's like a feedback loop. So if you have to continuously adapt, it's important that that loop is short, so you don't run out of patience. Actually, back in the day, I created a Windows tool for this kind of reverse engineering. It was kind of like Wireshark, but at the API level, so it could show you the socket communications, but also the encrypted stuff. So it would inject code into the target process and sit between the application and the crypto libraries, and intercept those calls and show to you decrypted.
Do you need to stop your antivirus?
Depends on the antivirus, because Frida uses some things that might, some techniques that might set off antivirus, but
it look like that on the drawing.
Right.
You set up things in another program.
Yep. There's several ways you can use Frida. You can also load it with LD preload or a similar mechanism. You can, if you have the source code of the application, you can also modify the application to load the library or the agent. Well, it's called a gadget in that case. But that's what Frida is. Technically, dynamic instrumentation toolkit just means it's a scriptable debugger kind of. But unlike a debugger, the code is running inside the target process. So you're not sitting on the outside, you're sitting on the inside. So you're in the context of the process, you can do anything that process can do, which simplifies a lot of things. And it's scriptable, but you don't have to. You can also use it from C++, because it's highly modular, and the high-level API that we're going to use today is just a composition of the different components that you can use in isolation. And it's open source, and it works on the major platforms. And that's continuously expanding. So QNX was not done by me, for example. And so the MIPS support was not either. So basically, you would use Frida for reverse engineering, programmable debugging, and so on. But the key here is that it should be should allow you for a rapid development of new tools with a short feedback loop. So I think we've talked enough. We should actually show it. So to do that, we're just going to create a really tiny dummy hello world application. Yeah. So what we're going to do is that we're going to have this program. Hope this is readable. Oops. It's going to have a variable n. It's going to have an infinite loop that calls a function f with n incrementing, and it's going to delay by 1 second between each call. And then we're going to create this function f, and it's going to just printf the number that you gave it in n. And we're also going to tell you that f is at this memory address. We assume that it's not inlined for this example. So we're really in tight control here. We just want to easily to see what's going on without starting with a really complex application. So that's why we're writing this now. And UniSTD for sleep. Okay, hopefully. Okay, so we have this program, it's running, and it's calling that function every second with an incrementing integer as the argument. Okay, so now let's use Frida. So we'll use the Frida Python bindings. There's bindings for several languages, but for here we're just going to demo it with the bindings. The Python bindings, they look the same, pretty much just adapted to local conventions like camel case in Java or snake case in Python. So yeah, okay, so session, Frida, attach. Can you give it a PID or a process name? Here we use a process name, hello. So then we get a session, and on this session we can create a script. So session, create script, and here we give it some JavaScript to run. Okay. And then we're going to load the script, and then we should just block so we don't terminate. If we do, it will undo everything. So, okay. Yeah, we obviously need to load the script as well. So called HJS sources f read. And here we load it from a file. Okay. And then we're going to create this agent that we're going to run inside this other process. And we know that this function is at this address. ASLR might make it end up at a different address, so that's why we're printing it out. We could also use debug symbols, or if it was exported, we look it up that way as well. But here we're just going to use the address. So interceptor is an API in Frida that allowing you to intercept function calls. So give it the address of the function that we want to intercept calls to. And then we define a handler for onEnter when it's called. You could also define one for onLeave when it's returning, but we won't need that. And here we have access to the argument list. Well, assuming that it has a default calling convention, and there's some assumptions there, but you can also access the registers, but I'm jumping ahead of myself. So we can do console log here. F called with n equals args 0 to int32. Okay, so we have written an agent that attaches a probe, so to speak, to this function. So whenever it's called, this line of code here gets executed synchronously, and it's just going to log the first argument n.
So basically that's a pthread pthread touch, a pthread poke text, and and set the memory rights or load the DLL, or what does it do in the context of the
Right. That depends on the platform. So on Linux currently, we hijack a running thread and make it call pthread create to create our own thread. Then that calls DL open. But on macOS, on iOS, and I have written a dynamic linker where we can do it from the outside of the process and just map our library into the process without it having file system access. So in case of sandbox processes. On Windows.
thread on Windows?
Yeah, exactly. But for Windows, we want to have more mechanisms. So we have written a Python program here that just attaches to this process, loads this agent, and runs it in there. Hopefully it will work. So let's try it. Okay, so we'll just do Python explore.py. And if you pay attention on the right, hopefully, yeah. So you can see that our probe is getting hit and is logging the argument. So you can see that they're in sync. It's happening in real time. So yeah, now we know what n is, the argument to this function. But actually, we did write some boilerplate code here, and that was just to show you how you can use the Frida's bindings. You don't have to write this kind of boilerplate for every use case, but this is just to show you how you would do it. So you could use Frida's REPL. So you do Frida, name of the process, and L-L for load and the agent. And here we go. That's much simpler. I should have set up my environment better. Okay, so we have that. And I just want to show you one thing. We can actually change this and save if you pay attention now. So it reloads the file. So it monitors this. The REPL will monitor this file, and whenever it changes, it will reload the script. So that means you have a short feedback loop. You can adapt your instrumentation and instantly see the results. Is this code readable, by the way, for everyone? Okay, cool. So the next thing you might want to do is modify an argument coming into the function. So what you could do here is that you can do args 0 equals, and you could take the existing value and add 9,000 to it. And if I save this, well, actually you'll see here that the function is seeing a different argument now, and this happens at the edge of the function, so we don't actually change n in the parent scope, just to be clear. So we don't change n here, because now if I stop the REPL and you pay attention on the right, it's back to normal. So the instrumentation is reverted. So if this goes away, the agent running inside will detect it and will revert everything. Okay, so we know this program pretty well. So how about speeding up time, for example? So we know that it's calling sleep, and that's what it's using to drive its clock, so to speak. So what we could do, let's just load the agent again, is that we could, I'll just remove this code. We could do interceptor replace to entirely replace the implementation. And now we need the existing implementation to replace. So we'll do module find export by name. And we know it's using sleep, so we'll look that up. And then as the replacement, we'll create a native callback. We give it a function. It's given duration to sleep. That's the first argument. We'll do something here, and then the return type is void. That's probably int, actually. Oh yeah, that's level. It's a uint and a uint. Okay. Let's accept an uint. And then here we could use Frida's thread sleep to just sleep for, say, 50 milliseconds. So if I save this, and you pay attention on the right, it speeds up.
Did you change the PLT or global offset table or something?
No, I patched the implementation, the beginning of the implementation with a jump.
All right.
So yeah, inline hooking, basically. Yeah, and we can revert it again, and it's back to normal. Another thing you might want to do is to call that function yourself. That could be useful for fuzzing, for example, or finding bugs, but also to, if there's a custom decryption function internally, you could call it to decrypt something. So we can do new native function. And we need the address of this function that we want to call. And that's here. And we know it returns, the return type is void and the argument type is int, one int. And here, I could create a loop. Okay, so if we run this agent, you should, if you pay attention now here, we called 5 times. If I reload the script again just by saving it, it will happen again. So now we have a way to call functions. That's how you do that. And these scripts or these agents that you create that run inside target processes, they can also communicate. You can also communicate with them, so they can send and receive messages. So I'm just going to show that quickly here. So you can do RPC exports equals, and then, for example, call, well, just f. Give it the argument n, and it just calls f with the n you gave it. Okay, and now if we go back to our Python program, after we loaded the scripts, we can do script exports. That's a magical object. So whatever you access on it, it will be a function, a generated function. So you can do agent.f one, or for I in range 10, call it with I, and then block. Actually, we don't need to do that here. You could just exit. Okay, so we have this script. It declares a native function to call this function in the process memory address space, and then we export a function f, and then on the Python side, we just, on the script, we do exports.f to call the function. So if we try that, and you pay attention on the right, it's called 10 times here. So you could, that way you can expose APIs and call them from Python or another language. So you turn your existing processes into services if you want to play with them. Okay, so now we've covered the basics of how to use Frida. But Frida also has some tools that you can use. I showed you briefly the REPL here. You can also, I can just show it again. So you can do things like this in the REPL as well, just paste it in. And if you want to call this function here, just you can play around. And here you have code completion for the Frida's API. So one thing you might want to do now, okay, so we're now done with our own program. We can switch to some existing software. So say we have Telegram on macOS. We might want to know what kind of files this program opens. So we could use Frida trace. And we can say Telegram-i open. So we'll trace all functions that are named open in the Telegram process. Okay, and now if I switch to Telegram and I tap or click around, you should see that it's actually calling open. And the colors here are depending on the thread, which thread is calling the function. So you can get a sense of how this application is designed with threading. One thing you might want to do is interact with Objective-C APIs. But I'm going to show you one thing first. So this Frida trace program here, when you run it like this, -i open to include a function in open, you also use globs. It will generate a directory called handlers on the file system, and each library that it matches a function inside will get a directory, and each function will get a script. So you can actually go and edit these scripts. So here I've edited the open.js, or I have, and we can say hello NDC open, and if I now just go here and trigger some activity, so it live reloads too, so you can adapt this instrumentation as it's running. To save time, I'm going to cheat a little bit here, because I want to show you that you can actually call functions on Objective-C APIs as well, not just native APIs. Because Frida has an Objective-C integration that is built on top of these things that you already saw, native function, native callbacks on, to give you a dynamically generated language binding. So it will use, for those familiar with JavaScript, we use proxy objects to dynamically generate things or look things up when you ask for them. So in Frida, you can use obj.c.classes and the name of the class, and you get a dynamically generated binding. Okay. So actually, let's just write an agent here. So we'll attach to the open function. Okay, so whenever open is called, we'll do open path equals, and then we can create a variable for the path. So and we can do memory read UTF-8 string to dereference the pointer. That's in the first argument. That's the pointer to a string, and we can log that. And so if we Frida Telegram, use the REPL again and load the script here into that process, and tap around. Yeah, you see it's working. And now you could, to show you that you can integrate with Objective-C APIs, let's play with, let's try Apple's speech synthesizer, which is available as an API. So we'll just do Obj-C classes NS speech synthesizer, assign that to a variable, and then we're going to create an NS auto-release pool, which is a requirement for using this API, or using such APIs. We're going to instantiate a speech synthesizer. We're going to pick a voice, and then we're going to set a voice, and we'll release the auto-release pool. But we have this synth here as a variable, and then in the inline hook, instead, in addition to logging, we'll also make it speak. And that will have a last speak, so it doesn't to rate limit it a bit. Just try to fit it on there. Okay. Let's turn up the volume and try this.
/users/oleavr/library/group contain /users/user/var/nsurlstoraged/dofsedata.bin.
Very useful. But the point is just to show you that you can use Objective-C APIs that already exist, and you're running in the context of the application, so you can combine things. Like, when the application calls a certain function, you can do something else using an existing API. Yeah, and I was showing this on a Mac, but to prove that Frida runs on multiple platforms, I'm going to show it on iOS too. So here I have a jailbroken phone, but you don't need a jailbroken phone to use Frida. You can still repackage the app and add Frida to the app. Same with Android. So I'll fire QuickTime Player. Hopefully I'll be able to stream the screen or show the screen live. Okay, cool. So there's a command called frida.ps. Oh yeah, I forgot to say, if you pip install frida-tools, you'll get these command line tools. If pip install Frida, you just get the API that we used before. Okay, so we can use frida.ps, and we can say, well, just no arguments, it will list the processes running on this local machine. But you can also use, well, if you look at Frida LS devices, you can see what kind of devices Frida knows about. So it's a local system, the iPhone is connected, and you can use Frida-ps-u to just pick the first USB device, or you can use -d and the ID you got here to pick a certain one. And if I run this, you'll see the processes running on my iPhone here. And you can use -a to list applications, and I for installed, so not just the ones that are running. And here you have all the processes running at the top and the apps installed. Okay, so I should have a Telegram app installed on my phone here. So we can use Frida trace -u USB -f to like spawn a program instead of attaching. You can either give it like bin ls, or you could give it without starting with a slash. It means it's an application, so it's an application ID. So here, Telegram, and it will include open. So if we run this, it launches the app, and you can see calls to open. And yeah, you can. Again, you can edit the handlers here and change it. Hello NDC from iOS. And if I tap around here, yeah, it's reloaded. So the next question you might have is, okay, now we know that someone is calling open, but who is calling open? So we can add some code here. called from new line tab, say thread backtrace this context. That gives us an array of return addresses. And then we can do map on each. And we can do debug symbol from address. And we can join, that turns each one in the array into a debug symbol if it's available, or a placeholder if not. And then we join these with new line in tab. If I run this, I'll save this and go here and tap a bit. Yeah. So you see hello NZ from iOS called from and the backtrace. Okay. I'm just going to jump slightly ahead and show you what that might look like with a different app. Oh no, I'm going to do that next. Okay. So run it again. And here you'll see that you'll also notice you'll notice Objective-C APIs typically in the backtrace, and then that might give you a hint where you should be tracing next. So you can then go and trace those APIs and learn more and more now about the application. Another thing you can do is to look at registers. So if this function has a very weird calling convention, you can look at any of the registers. So you can do like this context x0, for example, to access the x0 register on ARM64. And here you go. And if I just dump the whole object with this context, you'll see all the registers that you have access to. So that means you can deal with also weird calling conventions, or if the compiler came up with a calling convention on its own because of optimizations, you can still look at registers. Okay, so let's look at another commercial application. So Snapchat uses encrypted communications. So let's Frida trace that. And I know it's using SSL read and SSL write. Those are part of the security framework on iOS. That's what it uses under the hood for encryption and decryption. Yeah, it's calling it. And what you might have noticed earlier is that the generated handler actually logged things for you, like the argument to open. You didn't actually have to write the code. That's because there's a really ugly hack there that tries with man to look up the man page and then does a regex to find the signature and generate some code based on that. It's not pretty, but that's in Frida tools. So Frida trace is just 900 line or something Python program. It's pretty small, really primitive, and it has like a poor man's API lookup there with man pages. So that doesn't work with SSL read here. But if we go and look up the docs, which we won't have time for, we'll learn about the signature. We could also reverse engineer it if it wasn't already documented. So I've already written this.
Do you set a hardware breakpoint on SSL read, or do you inject an illegal instruction, or no?
It's the same. We rewrite the beginning with a jump or a branch, and then if we can't allocate code near enough, we'll jump through a header nearby, like find an ELF or a macOS header and trampoline through. So I have a handler here for SSL read. It gets the pointer to the buffer to to read into as the second argument, and it has an out argument in the fourth. And then when it returns, if it's successful, we can read as much as it returned in the processed argument that was processed, and we can dump that with hex dump there. Should also do the same for SSL write. Yeah, there you go. So if I now tap around a bit in the UI here, say something like that. Yeah. So you can see it's calling SSL read. This is the decrypted, the thing they got from the server. So you could do the same with the OpenSSL APIs. And if the process has statically linked OpenSSL, that's a bit harder because you need to find the functions. But you can use static analysis tools to figure such things out. Okay, so another thing that's quite common is jailbreak detection in mobile apps. So say Deutsche Bank's app, for example, it's a random example, does this. And usually these jailbreak detection schemes are using lstat indirectly to look for a file, the presence of certain files. And here you can see it's looking for bin bash, user sbin sshd, etc apt, etc. So, and it's showing us a jailbreak destroys the security layers designed to protect your personal data on your iOS device, etc. So this app detected that there's a jailbreak, that the system is running on is jailbroken, and now we could use Frida to bypass their anti-jailbreak scheme. And usually then you'd start by looking at the backtrace where lstat is called from. Then you'll find their function that calls, that's doing all the checks, and you can just replace the whole function with a return true if it's like it's jailbroken. And show you that you can also instrument Java APIs on Android. So that will look like this. You do Java perform to attach this thread to the VM, and then you can use Java use and the class name. Then you get a wrapper for that, and you can do a name of a method dot implementation equals on the function, and then you replace the whole implementation of that Java method. So that's how you would do hooking on Android with Java APIs. But you could also use the interceptor that I already showed you for native APIs. One cool use case is injecting errors into applications, fault injection. So you could do like, this is not very readable. Let me just copy. So this example iterates over connect and connect no cancel. There's two versions of connect on 32-bit on macOS. And then it's defining a native function for connect, so it can call connect itself, and then it replaces the existing implementation of connect. And then in the replacement here, it will look at, well, the first argument is socket, next is the address, and the third is the address length. So it reads out the address family from the address, and then if it's inet or inet6, reads out the port, and if it's one of these ports, then it does this erno is econ refused, a return -1, and so it just returns right away. However, if it's not, then it's going to call through to the original connect, and that way you can create like a software firewall inside the processes that you want to debug to make them think they're firewall in certain ways. And to trigger interesting code paths. And this is also great for testing, for like not reverse engineering, but for testing. Another thing that's interesting is there's an application that's calling receive. It's receiving data from the network, and after it's received the data, it might be processing it and then calling receive again. So it might be, it depends on the architecture of the application, obviously, but that's a simple one that will be what's happening. So you might want to know what's happening between two successive receive calls. And I have an example here where that's done. So here we combine two different Frida APIs, interceptor that you saw earlier. So whenever a receive is called, we use a stalker API to start tracing this thread. And then when receive is called again, we stop tracing it. And then we have an execution trace. And here I have just visualized that with the tool. With this is the agent and the other side that's controlling it. So you can also build code coverage tools this way. But what's interesting here is that you could correlate it with what you actually receive from the network. So you receive one packet, you record the execution trace, and you receive a different packet, record it, and then you can diff the two and see where they diverge. And then you know that, okay, here in the code, it's parsing that part of the packet. So you might want to go there and look at the parsing logic to understand the protocol. Or to find out how you can, if you're building a fuzzing tool, you could use it to guide the fuzzer to have as much coverage as possible. And I just want to show you a proof of concept I did some years back. So here, this is a colleague with me, a friend of mine. We were sitting on a plane trying to come up with a fun way to show Frida, and so we took the globe thing from the Google Arts team and put a UI here on top. We're using the Frida API and showing you the data socket communications, and also the different file descriptors it knows about, and the types of sockets, etc. But what we also did is whenever there's an IP address observed, it will do a GeoIP lookup and plot it on the globe. So you could actually get a visualization of where the communications is happening. So this is with a Spotify back in the days when they were peer-to-peer. I don't know if they are still, but so now if I go and play music here, if you pay attention to the globe here, it lights up. So it starts making connections all over Europe. Yeah, this is an example of a fun tool you could build, or a useful tool. And then there's another one called Crypto Shark. It has nothing to do with crypto, but it couldn't come up with a good name, so it stuck. So it's a Qt app written using QML, using Frida's QML bindings. So it has a process selector here. These icons come from Frida's API. That works on iOS too. So here you have the list of threads that are running in this application. In this case, it's Chrome. And these, I jumped a bit too far now. These threads are tagged dynamically based on the APIs they're using. So if a thread is observed with interceptor that you saw earlier to call file IO API, then it's tagged with file. If it's observed to call with a networking API, then it's tagged with net. So this way you get a sense of what the different threads are doing. And then you can use the code tracing API that I showed you quickly with all calls between two calls earlier to actually follow that thread. And here you see the functions that are called and how many times. And these are not exported. These are just internal functions in this program. And it's classifying them as functions just because they were the target of a call instruction on x86. And then you can click around here and look at the disassembly of the functions that it's calling. And you can also do add probe like I did here, and you see logging whenever it's called. And you can click on that, and you can edit the logging code, and it's updated live. So the idea is that you can look at the internal and the application, what kind of functions are called. You can maybe interact with the UI and see what new functions are called. And this could be taken further, and it could have heuristics that will look at arguments and try to guess and say it saw an MPEG header, a pointer to something that looks like an MPEG header. Maybe it can show you, hey, there's a media stream happening here in this process. Maybe you want to look at here at this point. There's many things you could build to help you reverse engineer. So yeah, I think I'm out of time. So any questions?
Where does the name Frida come from?
It was originally free IDA, because IDA is a static analysis tool. So it was kind of the ambitions were like, I will have static analysis. But I started implementing dynamic analysis first, and static never happened. And later, I'm glad I didn't, because there's a friend of mine, a coworker actually, who's working on Radar, which is a static analysis tool competing with IDA, open source. So we have R2 Frida now. That's a plugin for Radar, where it just gives you Frida inside, so you can combine static and dynamic analysis. So yeah, that's where it comes from. And it's, yeah, it was also a pun on Ida, the static analysis tool. Ida is a Norwegian female name, and Frida, the sister. So they will like complement each other, because one is static, one is dynamic. Yeah. Yep.
So you showed Frida working on Android apps, but what about native binaries running on Androids?
Yeah, that works too. Cool. Same way with Interceptor that you saw. And
where has this tool been my whole life? This is amazing.
Thanks. Oh, I should show you. There's a website, codeshare.frida.re, where people are encouraged to share their creations, and there's already a lot there that you can learn from. Universal Android SSL pinning bypass, iOS data protection, look at that. Frida anti-root, AES info. There's a lot there already, but that's a great place to learn.
Codeshare.
Yeah, codeshare.frida.re. And the APIs I was using is on the website and docs, and then API reference, JavaScript API. And I recommend the modes of operation here, which shows you they can use Frida different ways, like injected as we did before, or embedded in an app, or LD preload, or the different mechanisms. So,
question. How do I configure my computer OS Linux to not allow for this?
I wouldn't worry about this, because you need to have you need to be able to execute code on the machine. So
sure, but this
this
can
is
be used by other. The same techniques can be used by other applications as well. So
yeah, but this is just like GDB. It's a debugger. You could use it for nefarious things if you want to, but it still needs someone to run it on the host. So.
Text segment. Just verify that it's not changed, I guess. Because the text segment on the instrumented process needs to be fairly severely changed, I guess.
If you use right.
Trampolines and all the functions. So
if you use Interceptor, it will be visible. But if you use Stalker, it will not be, because then it will actually not touch the original code. Then it will be just in time compiling the code that it would have been running and pretending that it's running that code. So that's to make it hard to detect that I did that, because I was reverse engineering some Apple stuff, and they had some anti-instrumentation stuff. So yeah, it depends. But there's a lot of. I was seeing that mobile apps are starting to implement anti-Frida now. Some games have it. But the good thing is that your instrumentation code runs before the application's code always. So you can always counter. When they look for Frida, you can use instrumentation to actually make it look like Frida's not there. So
What
So-
do they typically do? Do they check that foreign language library has been loaded, or?
That's one way, but that won't work on Mac and iOS because we have dynamic linker there. But they might connect a local host to a certain port, which is if you're deployed on Android or iOS, it will be listening there by default. You can change the port. Or they might try to connect to all ports and try to send a hello and see if they get a response. Yeah, it's futile, I think. It's a waste of time because, yeah, no, long story. Okay, any final questions? Yeah.
No one can have no one come after you with a dozen lawyers and big scary file documents?
No. It's also used by Fortune 500 companies that, but sadly not all of them are allowed to contribute because they think it's a hacking tool. But it's not a hacking tool. It's a dynamic instrumentation framework, a toolkit. I mean, so, yeah. So no legal trouble so far. I mean, yeah. But there's nothing illegal about it, in my opinion. So. Okay. Thank you.